Good afternoon, everyone. Welcome back after lunch. Everyone's feeling tired? Maybe not? Well, just before we get started, I just want everyone to, if you please ask questions via the app. So there's the app, you can actually ask questions in there, and we'll put those questions to Shannon at the end of the talk. But our next speaker is Shannon Hartley. Shannon's from CENET, which is part of the Catholic Education Network, as I said. Yep. He's been in IT for over 15 years. He started off as a humble sysadmin, but I think that's a pretty glorious job, sysadmin. And now he's an IT security architect. So today he's talking about the identity trilogy. Is this our greatest threat? So please make Shannon welcome.
G'day everyone. That's not actually the title. That's it there. CNET amplifies impact, automating AusCert notifications to pay forward insightful reports. But we'll let that slide this time. But welcome, thank you for coming along. It is now afternoon, as you mentioned, and we've had some lunch, so if you are anything like me, you're probably all about to go into a nap. So I won't be offended if you want to move about, grab a coffee, have a stretch, that's fine. If you do fall asleep though, the people on the cameras might take your photo and post it online, so be warned. For those that do stay awake, there will be question time at the end, and you can use the app, but if you are confused at any point and need a clarification, just throw up your hand and I'll take a question as well. So my employer, CENET, or Catholic Education Network, has about 38,000 IP addresses and 1,500 top-level domains registered with our good friends at AusCert, roughly. And as you well know, AusCert looks for these items in the cyber threat intelligence that they're able to gather, and they send us an alert via email each day that something is found. So CENET operates somewhat like a managed service provider. For my team, our job is to process the intelligence we receive and pay it forward to the appropriate organisation in a timely fashion. I had a quick look over the last 12 months or so to work out what this looked like for CENET in terms of numbers, and what I found painted an interesting picture. In that 12-month period, we received just under 1,000 sensitive information alerts and about 1,200 member security incident notifications. Rounding it out, AusCert's service provided us about 2,000 alerts per annum. And that works out to be very roughly 8 alerts each workday of the year. Now, that doesn't sound too bad really, but for the poor security analysts sitting there wondering why they signed up to become a mailbox administrator, that can be tedious and unsatisfying work. So I hear. Now, these numbers may not even be a drop in the ocean compared to some large organisations, but for a small team of 1 or 2 people, it can feel a bit like a one-sided game of dodgeball. But setting aside job satisfaction and manual handling errors and the such for a moment, think about the impact in terms of time and money. Assume an average of 15 minutes to manually process each alert. Suddenly, you're talking about 25% or a full quarter of a skilled role's time being sunk into reading emails, looking up registers, copying and pasting text, and writing advisories. Assume also a median salary for a security analyst. That's more than $20,000 per annum spent on something that can be done in a matter of seconds by an automated process, thereby freeing up the analyst to use their skills in more rewarding ways. That was our reality at CENET, spending time every day manually processing alerts, and we were keen to do something about it. Being here today, I'm going to show you exactly how CENET has automated processing of AusCert's alerts. I'll cover the value of data, ways of turning raw point-in-time data into textual and more consumable, insightful information. And together we'll take a deep dive into the processing logic for the sensitive information alert, so you can see exactly how that works even for encrypted attachments. Along the way, I'll also raise some important considerations that may influence how you yourself would approach this problem. Ultimately, I'd love to hear feedback from everybody to help us improve on what we've started building for CENET. and hopefully we'll connect with some of you over the course of the conference. First, to make sense of some of our design decisions, a basic understanding of CENet's operating context is necessary. And no doubt you've picked up that the Catholic Education Network supports the Catholic education sector, but it reaches further than that. Catholic education in Australia is just one of the many agencies providing service to our communities on behalf of the Catholic diocese. Catholic dioceses are kind of like regions, and they group parishes or communities across Australia. There are about 28 dioceses across the nation, and each diocese, through its offices, agencies and parishes, provides services to our communities. That can be things like religious rights, births, deaths and marriages, social services such as adoption, foster care, daycare centres and providing for those in need, through to supported independent living, affordable housing and employment opportunities, among many, many more charitable works. It happens that one of the largest services that a Catholic diocese provides is Catholic education, so schooling from K to 12. The education service of each diocese is in and of itself a large organisation with its own head office known as the Catholic School Authority and many branches, although I hear we tend to refer to those as schools. Collectively across Australia, through Catholic education and the other agencies of the Catholic Church, we're talking about the potential to reach and support well in excess of 1 million people. And it's a hugely diverse environment. Corporate offices, children, wide area networks, parents, mobile devices, financial transactions, building automations, and many volunteers and workers, and it's all driven on a not-for-profit basis. And people tend to want to travel, so operationally, the IT environment isn't constrained just to Australia. CENet services are delivered primarily to Catholic education within each diocese, and each Catholic school authority manages their own IT environment, including building out infrastructure and resourcing to support their branches' schools. There are about 2,000 Catholic schools across Australia, and being charitable or not-for-profit organisations, traditionally it has been difficult for a diocese to fund even basic IT resourcing, let alone specialised security resources. But once upon a time, in a land far, far away, some of the dioceses banded together and they established a company to provide a core set of services centrally. A shared service like this can do things once and provide the benefit to all of those dioceses. It's a much more cost-effective approach, and thus was born CENet, or Catholic Education Network. Today, 17 of the Catholic dioceses in Australia jointly own CENet and benefit from the IT services and support we are able to provide to them by virtue of being an extension of their teams. And this is why we are receiving, processing and forwarding AusCert's alerts to various organisations across Australia. In the same way that AusCert aims to improve security for the Australian population, CENet has a mission to uplift the cybersecurity posture for Catholic education in Australia, delivered in part through delivery of security services and in part through fostering cybersecurity collaboration and awareness under the badge of the Cybersecurity Network, Catholic Education Australia. The conference theme here today of Pay It Forward and the spirit of open collaboration in this security community is why I, on behalf of CENet, feel truly honoured to be presenting here today. More specifically, and forming the remainder of the content for this presentation, is CENet's objective to provide an automated security incident notification service. You could say we're committing a sin, irony intended. This service aims to reduce noise, deliver timely and actionable cyber intelligence, be more easily consumed by the end users, and evolve from that raw point-in-time data to more insightful information. So without further ado, let's step through how CENet architected our solution. I don't know if architected is a word, but I'm sticking with it. We were already receiving the email alerts from AusCert, and that handsome devil there is me manually performing lookups and forwarding emails. We also already knew who we wanted to get that intelligence to, but we needed to replace the slow, error-prone and bearded individual in the middle with something more efficient and reliable that doesn't go on holidays or accidentally hit the snooze button in the morning. Fortunately, around the same time, we were procuring a SIEM system, so Security Information and Event Management, and that system included some SOAR functionality, Security Orchestration, Automation and Response. So in it went. Now, we also wanted to be able to enrich what we received from AusCert and in turn what we send to members with data from other sources. And that's really no problem. We just add other plugins to grab the bits we need. At this point, it's starting to look complete, but there's still a critical piece missing. The SOAR platform isn't intelligent, and don't worry, I'm not going to say the A word. The SOAR platform doesn't intrinsically know the correct person to send the intelligence to. It doesn't even know what organisation they belong to. All it has is an IP address or a domain, and really we're missing the reference data for the source system to be able to do a lookup and map that data, that domain or IP, to the organisation that owns it. So we took the 1,500 or so top-level domains that we manage with their corresponding owning organisations and entered that into the source system. But we hit a snag straight away. The product has a limit of returning only the top 1,000 results of a query. We started thinking of other issues as well. What if one recipient wants to opt out of receiving a certain type of notification? We need to be able to store user preferences. What if we get emails about the same vulnerability? How does the system know if something's been through already? And how can we capture information over a period of time and not just the current point in time? It quickly became apparent that to enable our solution to evolve, we needed to give it a memory. So a memory to store the data the system needs to answer those questions as they arise. So in went an external database. And from this point, things started humming along quite nicely. I'm going to unpack each of these boxes in a little bit more detail, starting with the inputs. Getting all of the notifications to land in a central mailbox was our first task. So the mailbox we set up is dedicated to the source system, but it can receive data from any source and be used in many different automations. To keep those emails that were coming in, because there's quite a lot of them, organised, the inbox rules are used to land those emails in specific folders or under specific labels if you're using Google's email. Those folders are polled by the source system, which fetches in new email messages from the folder designated for that particular workflow that's running. Next, the database. The database is the key piece of the solution that enables a lot more to be done beyond simply forwarding emails. An important architectural principle here is that of modularity. So having a separated database on a different server removes some of the risk involved with issues that may develop in other components of the solution. And it's easy to add and remove components as well when you need. Another very important principle is this: data is an asset. So while your hardware and applications can and should be easily replaceable to suit whatever your requirements are at the time, the data is what must be valued and protected. As an aside, our first iteration of the database was fundamentally flawed, and I can only blame myself for this. I carried in my mentality thinking about things from a networking and object-oriented programming kind of style, thinking that IPs and domains were database objects that represent their real-life counterparts and that their attributes always needed to be kept up to date. And this, along with building in a bunch of constraints such as not allowing duplicate IP addresses or subnets to overlap, meant that the solution could really only show the current time and not anything that had happened previously. So it didn't lend itself to longitudinal data. Now, at some point along that journey, I had the epiphany that I was thinking about it all wrong, not trying to create a solution that manages IP addresses or domains for an operational need, but what we're trying to do is create a record of observations. And that's typically what we're doing in security. We're observing the state of things at various points in time. And we're interested just as much in how they change over time as we are in their current value. So if you do go down this path, we recommend that your database is designed to hold observations about things, even if it's an observation about the same thing, but in a different point of time. Data engineers out there, if there are any, will probably have a proper name for this type of database. Does anyone want to call it out? No. Whatever it's called, it's being able to track the state over time allows one to answer more questions, such as, well, not just how many vulnerabilities do we have, but is the number of vulnerabilities we have going up or down? Or how long does it take us to resolve a vulnerability on average? Now, I've also mentioned reference data. So essentially your list of IPs and domains that you have registered with AusCert for them to monitor. And this is our simplified entity relationship diagram for the database tables that we ended up with. Now, for the most part, all the various entities have a many-to-one relationship with a parent organisation. In other words, each IP, contact, domain, I think I said IP address already, is tagged with the owning OU. And that's enough for the automated workflow to perform that lookup to work out where to send data pertaining to a particular IP address or domain. A final tip on the database, if you use some kind of low-code content management system to produce that, it can double as an easy-to-develop operational interface for you and your team to manage your security data, and possibly also link in with your service management and service delivery as well. So jumping now to outputs. With data in a structured format and armed with the appropriate logic workflows, it is then possible to generate outputs in almost any format that you could desire. So that might be STIX packages for your threat intelligence platform. It could be JSON objects for your API endpoint, or CSV files for your data lake ingestion, or it could be HTML embedded on your intranet. One can, in fact, send intelligence to multiple destinations simultaneously in different formats and all at machine speed. But remember to reduce the noise, otherwise alert fatigue sets in at machine speed also. And all of that intel will be ignored and your efforts will have been for naught. In CNET's context, with a very diverse network of endpoints and users, we opted to stick with good old email messages, at least to start with. So they're familiar to everyone and they're quick and easy to work with. But we did add a bit of CSS styling to give it a facelift and make it a bit more consumable. Here is an example of a report created from AusCert's alerts, and I'll zoom in on some of the features for you. So the first thing people will see is the traffic light protocol classification, which, according to the Forum of Incident Response and Security Teams, of which AusCert is one, should be in the header and footer of each page. So we're almost compliant there in that we provide that in the header, but in the footer we instead display a definition for each of the classifications, because with our audience, a lot of people don't even know what TLP is, so this helps improve the understanding. One can add all the pretty stuff too, so images and logos and rich text, but more importantly, using a template allows you to structure that information consistently, which makes it, again, easily consumable by people and optionally also by being passed and machine read by recipients. For those of you that operate across time zones, or you spend a lot of time analysing logs, which are typically in UTC time, you'll appreciate how inconvenient that can be, having to constantly convert across time zones. So we're pleased to be able to automate that and provide the end user with dates and timestamps in their local time, as well as UTC if that is their preference. One can tailor the messaging delivered to their end users. So that enables you to provide advice in a way that is appropriate to your audience. In our case, it's not always technical people, so we need to translate. One could even provide that output in multiple languages, automatically being mapped from the type of alert received from AusCert. Another consideration for our end users was the ability for them to very easily copy and paste data from that email into the spreadsheet tool of their choice, not Google Sheets, as we heard from the podcast guys today, although we do tend to use that a lot, so there you go. And using a HTML table allows that. We also consolidate the alerts that we receive from AusCert and summarise them in this report. So that way, each unique vulnerability by IP address and the port number is displayed only once, with the number of days since it was last seen. When vulnerabilities are remediated, the day since last seen gets older each day until after 30 days it ages out and disappears off that report. So it's a much easier way to quickly identify new issues and to confirm that remediation efforts have actually been effective. Another thing we allow our end users to do is to flag a particular vulnerability instance, and by that I mean a specific type of vulnerability on a specific IP address and port. We allow them to flag that with an ignore until date, and that moves the record to a secondary table in the report. So it's an acknowledged risk that is out of the way of the primary table, but still visible. And once that ignore date is reached, the vulnerability will return back to the main list and require a new exception to be requested. So this effectively promotes the review of accepted risks, which is quite important in a risk management world. For the sensitive information alerts, we chose to obfuscate the password, passing on only the first and last character. We felt that was a better choice than propagating leak credentials fully, while still allowing the end users to identify which service or account that particular leak pertains to. As part of the automation, we also perform a lookup on a directory service to confirm the email address is actually a valid user account and that it is active. And if it isn't, we drop it, allowing end users to focus on those leak credentials that represent the greatest risk. We have ideas for future enhancements as well. And one of those is a self-service cybersecurity dashboard for our members with selectable preferences, a curated set of analytics, and some super widgety widgets, probably some AI thrown in there as well, I'm sure. And exclusively here today, I can reveal the very first prototype of this dashboard. There may be some way to go yet. Jokes aside, something like that could be achieved by, again, using a low-code content management system overlaying your database. So again, if you control the data, the applications, interfaces, and hardware around them can be swapped around to suit whatever your needs are at the time. So up next, I'm going to take a closer look at the workflow used to decrypt and process sensitive information alerts. The SOAR product that we use is named Rapid7 Insight Connect, and it provides an extensive library of plugins. So there are pre-built actions for almost anything you could want, as well as integrations to most productivity and security services and applications. The solution that I've shown you here today isn't proprietary to Rapid7, so this concept could be implemented with any type of SOAR product, or if you really enjoy debugging, you could code it entirely in Python. So even if you can't find a pre-built connector, you can make your own custom actions using Python, as I mentioned. So this product allows us to visually build chains of actions known as workflows, such as you saw scrolling on the screen, on the previous screen. And I'm going to step through that workflow, which is for sensitive information alerts, so that you can see exactly what it does. So the first step here is a trigger that polls the mailbox folder that is receiving the AusCert sensitive information alerts. It does that polling every 15 seconds and creates a new instance of the workflow for each new email message. The whole email message, including the headers and attachment, is available to that workflow because the connector is using SMTP or IMAP protocols to connect to that mailbox. Next step there is to use a simple regular expression, which captures the thread ID from the subject line. We need that in a later step to look up the decryption key for this particular email attachment. Third, there's some Python code to perform some basic validation on the email, and as I'm looking at it now, that should actually happen prior to the previous step, so we'll add that to the to-do list. So that checks things like the sender is actually AusCert, the subject is, as expected, sensitive information alerts, and there's only a single attachment, and it has the right name and file extension. So last on the screen is a decision branch to check the result of that validation. If that validation failed, it takes the branch to the left and sends a notification to the maintainer of that workflow, who can then manually intervene as required. So sometimes AusCert will send out ad hoc messages with different subjects or file formats, and that's how they get picked up. If the message does pass all those checks, then the flow follows the right side branch where the attachment is decrypted and all of the credentials, which are effectively email addresses, are extracted. I'll come back to that step in more detail once we've gone through the whole flow. Last there, another decision to check if any emails were found in the attachment or not. If no emails were found, then a notification goes to the maintainer of the flow for manual intervention. That would indicate that what has been received isn't typical, so it needs some investigation. Usually though, emails are found in the decrypted attachment, and we enter a loop to process each one of those. So for every email, we look up the domain name in our security database to get the organisational unit that it belongs to. And we append that organisational unit's name to the email string, like a tag. If the domain isn't found, then we just tag it as unmatched. So in this loop is also where we check the email against our directory service to confirm it is a valid and active user, and if it isn't, we drop that email as noise. So you can see in yellow on the screen, the output of this step is an array of strings, where each string is the email address, first and last character of the password, and the organisational unit that the email domain belongs to. Finally on this slide, once again, is a decision branch to check if there were any unmatched email domains. If there weren't any that did not match, double negative, I know, then the left branch is taken. So effectively that does nothing but continues the flow. If some domains were found that we didn't have in our security database already, then we email those to the maintainer for, once again, manual intervention, and typically that is adding some newly discovered domains or ignoring some junk domains as noise. And then finally here, the two branches are joined back together and we continue onward, carrying forward the array of leaked credentials. At this point, we actually convert the array into one large string, simply because in a later step, it's much quicker to use a regex to match on the organisational units names than it is to iterate through the array using a loop. So that's a computational efficiency. You can see in yellow that now we have one long comma-separated value of leaked, comma-separated string of leaked credentials. And then the next two actions simply grab all of the organisational units from our security database, specifically their names and time zones that they work in. And then the last step on this slide grabs a snippet of HTML and CSS text, which we will inject into the output. In this case, the snippet is for the traffic light protocol that you saw earlier. And we have these templates pre-built so that they can be reused across workflows. The next two actions here are the same, fetching pre-built templates for the header and the footer, which will also inject into the output. And then finally on this slide, we enter a loop so we can work on one organisational unit at a time. So for this particular organisation, the first action uses Python code and regex to match and extract all the instances of that organisational unit's name in our long string of leaked credentials. The regex uses look-ahead matching, so it only extracts the email and password part that you can see highlighted in yellow, and it doesn't include the name of the OU itself. And that step outputs an array of all the matches found by the regex, which is all of the leaked credentials for that particular organisation. Next, in a decision branch, because maybe this organisation didn't have any leaked credentials that day, which for us is pretty rare, it actually breaks the loop and goes around to the next organisation. However, if matches were found, it proceeds to look up the contacts for that organisation. For the contacts, it attempts to extract their email addresses, and the last step there simply checks to see if those email addresses were successfully retrieved or not. If email addresses or recipients weren't able to be retrieved, then the maintainer is notified for manual intervention, but typically the flow proceeds down the right side path to generate the current date time, converted to the time zone of the organisation being processed. A final check is made at this point to make sure the workflow hasn't been set to maintenance mode for testing purposes before the output or our email report is constructed from those HTML, CSS snippets and the array of leaked credentials before it's being sent out to those recipients. So in real time, all of that happens in a matter of seconds or maybe minutes, depending on the size of the input we're receiving from AusCert. And all the while, I'm doing something much more important, like making coffee. I'll jump back now to the encrypted attachment. Now, I know some people will have that licked already, but some people may be stuck on that. So I wanted to share our approach. It's all about paying it forward after all. It does get a little too technical at this point for covering in a quick presentation. So I'll give a somewhat rushed overview of how to work through the problem, but do know that we're happy to share details and even code if you'd like to connect with us outside of this session. A point I'd also like to make is that this isn't hacking in like any kind of illegal sense. It's just programmatically performing an unattended login to the AusCert web portal and fetching the decryption key, just the same way you would do it interactively using a keyboard and mouse. And this kind of interaction is often referred to as robotic process automation. So first, understanding what is happening when you go to a web page in your browser. When you load a page or a resource on the web, it is known as making a request because you request that resource or the page from the server. A request can be of two main types. There's a GET request, where you simply want to connect to the URL and display it in your browser. And there's a POST request, which is where you also connect to a URL, but you're often sending some data, such as when you submit a form. The POST request is a bit more secure, hence it is used for posting data from a form. Often a website on a server, which is a whole collection of pages, will store some information about you so that you don't have to keep providing that same data each page that you load, and that is known as the session. And it lasts for a finite amount of time before being destroyed, much like my own memory. So take the AusCert member portal, for example, and notice here that I am referring to the portal before it was recently changed, so I haven't updated the slides yet. It's slightly different now, but the same process applies. So whether you're using a browser or running a script, when you first request a page on the member portal, a session is created so that you can track that sign-in state across different pages. So that first page also checks if you already have an existing session and if you are already signed in. If you aren't, you get redirected to the sign-in page, which provides you a form to fill in. Username and password, please. If you put the right credential in, then obviously you get redirected back to the page that you originally requested. You don't have to put that first URL in again because that's been remembered in the session. Now, all of that and more happens behind the scenes when you're doing it interactively with a keyboard and mouse. You can also do it using code. It's just a little bit trickier to work out how to trigger all of those steps, but I'll make an attempt at showing you how that works now. So walking through that same process, we first request the URL at the top of the page, which is the decryption keys page, but we get redirected to the sign-in page. The sign-in page is the GUI, but anyone can use developer tools in the browser to see the code behind it. Here you can see the HTML form with input boxes for username and password, as you would expect, and there are also some hidden input boxes that don't show up in the GUI view, but they are still visible in the source code. Now, when you hit submit with your mouse, those inputs and their values are, as we enter them, are sent in that request to the server. the hidden inputs and their values are also sent in that same request. What we can't see here is where the data is being sent to, because on that highlighted line, the form action is rather vague. But once again, anyone can use the developer tools to see the destinations of requests being made by their browser. So here in the type column, you can see all the redirects that took place to get to the sign-in page as an example. And you can do the same thing with developer tools open when you click on submit for the login form, and you'll see all the redirects happening then too. And ultimately you can reveal the destination of that form data or that post request. There are other tools you can use to do this as well, such as curl. They can make post and get requests in the command line, and you can see all the redirections taking place. So now, knowing what data to send and where to send it to, it's relatively simple to programmatically do the same thing. So here is a Python code snippet showing the exact same process, but obviously using code. So first, a session is started or continued, as the case may be. Second, a GET request is made to the URL for the decryption keys page. The information that is returned would normally be interpreted by your browser and displayed in the GUI. However, in this case, it's just returned and captured in a variable target page request. Also, the redirection still occurs because you aren't signed in yet. So what gets returned and stored in that variable is actually the HTML code for the sign-in page. Third line there, a parsing unit from the beautiful Soup Python module is used simply to parse that HTML that's returned into a format that can be easily searched within Python. And the final line here searches for and gets the value from one of those hidden inputs we saw earlier, which is all we need then to subsequently perform a post request to sign in unattended. Now, don't worry, I'm not going to show any more code. Instead, I'll do a one-page overview of what the robotic automation process would do to sign into the AusCert member portal, obtain the keys, and then decrypt the attachment. So the first step is to create variables for the data that are going to be submitted as the sign-in form, so form number 1. And those things include data such as the username, password, and auth state. The second step is actually to create a second lot of variables for data to be submitted, because there's actually a second form that you hit in the login process that you don't normally see because it's automatically submitted when you log in interactively. However, when you're using code, you need to manually trigger that. And that form has fields such as SAML response and relay state. So relay state is the variable that your target page that you originally put in is stored, so you don't have to enter it in again later on. Next is to start a session with the AusCert portal, request a page, the keys page presumably, and get redirected to the sign-in page. Once there, you can extract the auth state value from one of those hidden fields and update your variables for form number 1. Submitting those variables as a post request, you then get redirected once again to what I call an authentication response page. Now, once again, you can extract the value from a hidden input that is on that form and update the variables for form number 2. Then you submit another post request with those new variables, and this time you will get redirected to, assuming your login is valid, to the originally requested keys page, which was stored in that relay state hidden input field. Once on the keys page, you can use some Python code to obtain the HTML table to end up with a Python dictionary of thread IDs and corresponding decryption keys. Back to the encrypted attachment in the workflow, which you then decode from bytes, because it's an attachment, to ASCII ciphertext. You can then use a Python cryptographic module to decrypt that ciphertext. And as an optional step, as we perform, is to use regex to replace or obfuscate part of the password. So in our case, we leave the first and last character and replace everything else with dots. And then finally, you output an array of leaked credentials in plain text. Simple, right? Warning. So there are some disclaimers. There are some implications with the process to be aware of if you're planning on going down this path. And I should probably first point out that AusCert does not and should not be expected to support these kind of workarounds to access their service. All right, my time is up. I'll skip over this part. Very quickly though, make sure you do QA checks so that you're not missing anything. You should also be implementing MFA and securely passing the usernames and passwords, which I haven't shown here today, but I hear security is kind of a big deal here. And remember that AusCert can and will and recently has changed their web portal around, so that will break your automations. But there should be proper solutions coming along very soon in the form of an API, which I'm really looking forward to, which will make things a whole lot easier and you can skip all of that tricky stuff I was talking about. Key takeaways, and finally, any questions? Sorry, I had to wrap it up quickly at the end there.
Yeah, that was really a great talk. I mean, some fantastic automation you've been doing there, Shannon. But here's a little gift from the AusCert team.
Thank you.
There were some good questions in the chat. Obviously, it's not time to do that now, but Shannon's here until tomorrow, right? So,
Yep.
And it sounds like he's very happy to collaborate and share what he's been doing.
Definitely.
In detail.
Yeah.
So, yeah, please thank Shannon.
Thank you.